So our next topic will be looking at transformers, not these particular Autobots, but in relation to electricity. So the 4 learning objectives we're going to be focusing on in this unit are the recalling of the structure of a transformer and understanding that a transformer changes the size of a voltage by having different numbers of turns on the input and output sides. Explain the use of a step and step down transformer. Recall and use the 2 relationships given there around the primary and secondary voltage and number of turns in the primary and secondary coils, and also relate that to input and output power. So here is the first activity, a starter question. So pause the video now and answer these questions, and notice that the words required are actually jumbled up in the brackets at the end of each question. Okay, so welcome back. So let's look at these answers. So question number 1, electricity is made by generating it in a power station. Name 3 fuels that can be used in power stations. Okay, I'm just going to give you 3 examples, but you might be able to find more. So nuclear would be an example, maybe not in Malaysia, but elsewhere. Coal will be another example, and natural gas could be another possible source of power, or source of fuel from a power station. So most fuels in a power station are used to heat water, and it's used to turn it into something called steam. Okay, the wonderful steam generation of the 1900s driving the Industrial Revolution. What are the enormous fans in power stations called? They are called turbines. The generators contain large magnets inside coils of wire. This is because of a moving magnet inside a coil of wire that creates, as we learned in the last unit, electricity. Okay, where does the electricity from the power station go? We'll learn about more of this as we go through this unit, but it goes into something called the national grid. What do we call electricity which comes into our homes? We've done that already. It's called the mains electricity. We have 2 examples of using cells. Again, these are just 2 examples I've thought of. There may be possible ones that I have not thought of, which may be also equally adequate to answer the question. Okay, so I'm going to be environmental and go for an electric car, but also your mobile phone uses cells as well. And the power rating of an appliance tells you how many joules of energy are used every second. Okay, so that's the answers to the following questions. So what is a transformer? Well, a transformer is a device that is used to change one alternating voltage level to another. Okay, so here's a whole range of different transformers that you might see if you pull apart electronic devices. Okay, and this is the circuit symbol that you need to know. So essentially what it's saying is that transformers change a high voltage into a low voltage, or conversely a low voltage into a high voltage, and we'll see the reasons why we do that as we go on in the unit. So this is what a transformer basically looks like. You have basically a metal kind of core. You've got 2 coils, the primary coil and the secondary coil, which each have generation of different volts. Okay, and just breaking down that structure further, essentially consisting of these 2 coils of wire wrapped around a laminated iron core. Okay, so the primary coil has NP turns, okay, P standing for primary, and a primary voltage VP. And the secondary coil has NS turns, S for secondary, and a secondary voltage, VS. So how does it actually all come together and work? Well, when the alternating voltage, the VP, is applied to a primary coil of a certain number of turns, it causes an alternating current to flow in this coil. And this is known as the input voltage. Now this current, which is generated, okay, causes a changing magnetic field in this iron core that we've also got. And this cuts across the secondary coil, which has, again, a certain number of turns. So electromagnetic induction occurs, which we've learned about in the previous unit, which produces an alternating voltage in the secondary coil, okay? Because you're changing the magnetic field, it's generating an electrical current, and therefore a voltage. So when you think about this, why can a transformer not change the level of voltage output of a battery? So thinking about what we've just said, pause the video now and have a little think. Okay, so the key really is all about the battery. What's different to a battery compared to, say, a wire? Well, a battery produces a DC voltage, going right back to the earlier topics. This voltage will cause a constant direct current in the primary coil of a transformer. Okay, it's a constant current. So that means that the magnetic field would not change because the direction of the current's not changing. The direction of the magnetic field wouldn't change. This means that because the magnetic field in the primary core is not changing, this would not electromagnetically induce a current in the secondary coil. Therefore, there'd be no secondary voltage. So the equation that we use to work out the different voltages and required number of turns is known as the transformer equation. So the voltages or potential differences across the primary and secondary coils of a transformer are related by an equation. The primary voltage over the secondary voltage will equal the number of turns of the primary coil divided by the number of turns in the secondary coil. Or Vp divided by Vs equals Np over Ns. So what does this actually look like? Well, here's an example here. A radio runs off a main supply but needs only a 23 volt supply. The transformer has 100 turns of wire in the primary coil. How many turns are needed in the secondary coil? So you go back to the equation that we've just learnt. Vp over Vs equals Np divided by Ns. Okay, so it'll be 230 volts divided by 23. Okay, because remember, it's off the main supply. This is why we're saying it's 230 volts. Will equal 100 divided by Ns. Rearranging the equation, you get Ns that equals 23 times 100 divided by 230, which will mean the number of turns in a secondary coil will be 10. Okay, so now let's try and use this example to see if we've actually understood the equation. So we've just discussed that the potential difference or voltage produced by a transformer can be calculated by this equation here, which essentially says that the primary voltage divided by the secondary voltage will equal the number of turns in the primary coil divided by the number of turns in the secondary coil. Okay, so using the numbers given, okay, try and work out the secondary voltage produced. So pause the video now. Okay, so the first thing we have to do is work out what is what in this equation. Okay, so the primary voltage is going to be 240 volts. The number of turns of the primary coil is going to be 1,000 coils, and the number of coils in the secondary is going to be 50, and we've got to try and find out Vs. So what we do now is just basically plug in some numbers. Okay, so Vp divided by Vs. So we know what Vp is, it's 240. We don't know what the secondary voltage is. Number of turns of the primary is going to be 1,000, and number of turns of the secondary is going to be 50. Okay, so 240 over x will equal around about 20. Okay. So that means that X is going to equal 12 volts, okay? 12 volts if we rearrange that equation. And that's indeed the answer. So there's two types of transformer. There is the first one being the step-up transformer. And a step-up transformer, the voltage across the secondary coil is greater than the voltage across the primary coil. Because of this, the secondary turns must therefore be greater than the number of turns around the primary coil. Okay, and an example of a step-up transformer is increasing the voltage output from a power station from, say, 25,000 volts up to 400,000 volts. So if there's going to be a step-up transformer, there's going to be a step-down transformer. So in step-down transformers, the voltage across the secondary coil is now smaller than the voltage across the primary coil. The secondary turns must be smaller than the primary turns. So an example of this is to decrease the voltage output from a main supply of 230 volts to 18 volts, so it can be used by a laptop charger. So if you punch 230 volts through a computer, it's not going to like it. Okay, and this is where we get back to mains electricity and the national grid. Okay, so the national grid is essentially where electricity is created in power stations and then goes back to you through pylons to be used in your appliances. This particular power station delivers about 100 million watts of energy or power. If 230 volts was used, which is the same as our mains voltage, what current would flow through the wires? Okay, so pause the video now and have a little think about that. Right, so you should have worked out that the current you'd end up getting would be in the region of 400 and say 30,000 amps. That is quite a high ampage, okay? We'll just look at that previous video, what happens when you put a current through a wire, which is rather thin, like the ones in your appliances. So what do you think is going to happen if we use that current? It's going to burn everything down. It'll just be a complete chaos, okay? So power, you can either have a high current, low voltage, which would be the case we've just looked at, or a low current and a high voltage. So which method do you think is better for delivering electricity to your home through the national grid? Okay, so your task now is to discuss and explain that. Okay, so what you probably should have found out through discussion is that you probably want a high voltage getting to your home rather than a high current. This is where transformers come in. Okay, so the national grid is a system of cables used to deliver electricity power from power stations to us, the consumers. Okay, the higher the voltage used, the greater the efficiency of the energy transmission. So less energy is lost in the form of heat, for example. Okay, or sound. So lower voltages result in higher electric currents and greater energy loss to heat due to resistance in the cables. Okay, that's why the cables basically explode, okay, or they just melt, which isn't very efficient at all. Okay, so what happens is that you end up having a high voltage, low current in the national grid. Okay, so at power stations, the output voltage of the generators is usually stepped up by transformers from, say, 25 kilovolts to 130 kilovolts. Okay, so that's what's going to be traveling through the pylons. Okay, and it can be further increased by 400 kilovolts for transmission over long distance pylon lines, if need be. Okay, however, when it gets to your home, the voltage is reduced in stages by step-down transformers to different levels for different types of consumers. Okay, so for example, factories and light industry, they require a bit higher voltages, whereas you in your home, 230 volts is fine. So the lowest level of 230 volts is used for us in our domestic use. Final step-down transformer will be at a substation within a few hundred meters from each group of houses. So just to finish off, here are some examples of exam questions which you would be expected to answer. There are 7 questions, so I want you to work through them at your own pace. Okay, I have provided answers at the end of the video once you've completed them, just to check if you're on the right track. Okay, so these are the answers. Okay, I'll just leave them up for you to read at your own leisure. Okay, so this is the first question, around question 1. Okay, and then we have the second, third, fourth, fifth, sixth, and seventh answers. So hopefully you got them all correct. If you didn't, obviously you need to go over your notes again and then come and see me to discuss any problems you are continuing to have. Okay, this finally just some basic ideas around the topic. So transformers change voltage and current. Transformers only use AC, not DC. Current warms transmission wires, so you don't want a large current traveling through. Step-up transformers increase the voltage. Step-up transformers decrease current, and vice versa. And the energy is wasted in terms of heat, for example. So power depends on both current and voltage. At high voltage, the same power needs less current. Current mention turn ratio related to voltage change. Or you use a correct mention of turn ratio related to voltage change. A smaller current in a wire produces less heat. That's why we travel with high voltage, low current in the national grid. Okay, so when you use a higher voltage, the current is lower. With lower current, the amount of heat produced is less. If less heat is lost, the efficiency is greater. You correctly use the equations, and less heat is lost because the current is lower. So if less heat is lost, you have more efficient transport of power from the power station to your home, and current wastes heat in wires using a higher transmission voltage, and therefore a lower current saves more energy in transmission wire than it lost in the transformer. Okay, so that's a little summary of the basic ideas around this unit.